There's a lot of new projects happening in our industry, but our transportation infrastructure is old and needs a lot of work. And it's great hearing you guys talking about pavement preservation and rehabilitation. So as you're planning things to help fix our aging infrastructure, I hope you consider using 3D technology, specifically on the milling. It's not for every project, and I'm going to explain some benefits of using 3D. And I have a lot of slides to go through in a short period of time, so I made sure I drank a lot of water because I know I'm going to have to go soon. Oh, there we go. Cool, I have the same one in my pocket. So I'm the paving specialist manager, but I do focus also on milling, paving, compaction, and specifically asphalt. So who is Trimble Civil Engineering Construction Division? We have a lot of product solutions, part of our construction division, and they're basically broken up into three portfolios: software solutions, data management, and also asset and fleet management. Our site positioning solutions, these are kind of like the rovers that you see contractors out there checking grade with. And then, of course, the grading, paving, milling guidance solutions, including drilling and weighing solutions. We also have many OEM partners, machine partners, from attachments to skid steers to heavy equipment for grading, milling, paving, and compaction, and we're really happy to be a part of these partners that we have and working closely with them to help them for their machines for better guidance out in the field on your projects. So there's a few jobs that I've been on over the years. To be honest with you, I've lost count on how many 3D paving and 3D milling jobs. But see, these here are a few that we're pretty proud about. Started back in Telluride, Colorado. I think it was about 2009. Then we went into 2009, 2010 in St. George, Utah. It's very interesting on this project right here in St. George, because today Utah is really leading in 3D milling and 3D paving. They're extremely very busy with it, and it's not just specifications. I'm not even sure if there are specifications, but contractors have embraced the technology to provide better products and help manage their materials, and they've taken a big lead on that. There's quite a few more Pearl River constructors. I think that's where I first met your president, Darren, I think, right on I-15 with his milling company. I don't know who was more excited, Darren or myself, seeing the technology. I've been around him a lot, and I'm always really excited about it, but Darren was like a kid in a candy store, and it was very impressive, and it's part of his solutions for customers or customers that require 3D milling. Circuit of the Americas was a really interesting one too. It was a Formula One track that was purposely built for obviously for racing. We did a lot of 3D paving out there, and also when there was a change of design, they incorporated a 3D mill to change the grade without having to rip it all up and reprocess the material. My favorite one was the Corvette test track in Bowling Green, Kentucky that they did. It doesn't get more American than the Corvette test track. That was a great project that they did. And we were all out there. If you were at the U.S. Bank, the Viking Stadium, what some people don't know is underneath that awesome-looking turf there's an asphalt mat, 2 lifts of asphalt that Trimble 3D paving was used to make sure that it held the elevation, the requirements, and it turned into be a very awesome project. And these presentations will be posted, so there's links that you can click on whenever you download them, and some pretty cool videos about the operations. So there's 3 major factors in 3D milling. There's survey control, the 3D design, and the use and operations and setup of the machine. But for the sake of time, I'm going to skip the survey control side of it and focus on the 3D design and the machine itself. The designs have to be accurate and designed specifically for machine guidance operations. We want to have the data to be as accurate and representative of what you're building. If it's a road or corridor, that you use all the parametrics, the horizontal alignment, vertical alignment, cross-section templates, super elevations, any transitions, all that information that makes the road as accurate as possible. Also make sure that to have the design as the project will be constructed. You can see the difference. By the way, this is not to scale, but this would demonstrate a subgrade type design and a finished grade design. If the agency or contractor has just a finished design, it's kind of hard to go in and find where the tie slopes are, so make sure that the design is provided or built as the project will be constructed. Also make sure that it's built for machine guidance. If your minimum width for paving is 12 feet and you have slopes at 5 or 6 feet wide, it's very difficult for a paver to bend around these slopes. So we got to think about what the process is going to be when you're going to be utilizing 3D technology, whether it's milling or paving, that the surfaces are going to be at the proper width based on minimum requirements for the machine itself. We talk a lot too in this process about optimization or densifying the surface, and what that means is that we want to have the surface as smooth as possible through transitions. We see data sometimes that are kind of corded or segmented, and as the machines go over it, it's not totally smooth, representative going through, say, in the super elevated curves, and I'll show this in a couple other slides after what it means. And the other one too is that we want to make sure that the design, this is the design, not the actual final product, can meet or exceed your ARRA smoothness specs. If you have a goal of 40 or 50 or whatever your goal is, and your design can't break 100, we're going to have a problem, because we will do it accurately right or accurately wrong. So the system, the data gets fed into the machine, we follow our procedures for setup, and if the design can't meet or exceed your ARRA specs, you will get out what you put in. So pretty simple. So this here demonstrates a curve, and you can see we've got a little vehicle down here in our software going around the curve, and this is what they're seeing. You can see how all the segments are going through, and most softwares have a minimum cross-section that the surface can be built on, 25 feet. They can bring it down to 10 feet, 5 feet, or a foot. The problem is that the more cross-sections you put in to create that surface, the files get extremely large. But it's not uncommon for us to see, it's not uncommon for us to see data like this. And again, when the machine tries to follow these here, it's pretty hard to maintain a smooth surface. So densifying a surface means that you can increase the smoothness vertically. So you can set a tolerance, say, of a 1/4 inch. So every time there's a vertical change, we basically smooth out that area. And you can see the difference somewhat coming through here, that nothing's changing because the grade's very consistent, but it gets densified into the curve, hence having a nice smoother surface as you're going along. So that's really important when you're trying to achieve smoothness. So why use 3D milling and intelligent construction? To build better paving structures. So you can increase your production, hence lowering your cost by only milling what you need to mill. So if you're doing profile milling, we'll make sure that we take out all the longitudinal waves, the high spots, and basically get it down to where it's all averaged out and smooth. Depending on the spec of the project, you may have where you have to mill a minimum. So let's say you have a minimum milling that you have to have, say, of 1.5 inches. You can come back to a specific station, vertically offset, and just remove the areas that you need to remove so you get into the existing pavement. What that ends up doing is that you actually have a controlled surface that you can fill up prior to mainline paving, so it ends up having a more consistent structure all the way through. And that also includes if you're milling and you get delamination, scabbing, and it's decided to go down a little deeper, you can control that anywhere you want vertically and basically just cut out some big, perfect rectangles and fill it up more consistent. The other big thing that we see is if there's a failing road and you have to change your slope, we can put a design in and actually reshape the road back to what the specifications are calling for. And we're also seeing some areas, specific where I've been involved, is say in Louisiana and Mississippi, where there's potential for flooding, where they, instead of having a typical 1.5 minus crossfall road, they're basically changing it to, say, a -2% going all in one direction. So we call these kind of like what they call wedge jobs, where they're reshaping the whole road. So they'll use a mill to get a common foundation of the surface and then build it up with materials using a paver or whatever methods that they have. We can also mill complex designs, any transitions. Again, if the machine is capable of maneuvering around whatever you're trying to feed into it, we can do it very well. A mill is an awesome machine, and we're seeing a lot more people utilizing and taking benefit of what the machines can do. The other big thing is that there's no wire or string line required, so this also reduces costs of putting material or wire on the ground for vertical guidance. And one of the big features of that, in addition to being safer, is that it's a lot easier to manage traffic and trucks in and out of wires that's on the ground. So you eliminate a tripping hazard, and if somebody knocks over the wire or gets tangled up into it, it's a bit more costly to replace them back to grade. So here's an example of a 2D milling job on a 3D elevation paving job. Sometimes we see where where they basically what I call blow and go. They drop down into the cut. They'll cut lower, requiring some leveling course to fill up the material. In this situation here on this project, they actually went high. When they put down the first lift of asphalt with the 3D paver, it was pretty terrible. They were busting rock, and that's my folding rule down there, and it's probably about 10 millimeters, and it was pretty bad. I saw the engineers looking at it and kind of questioning what they got themselves into, because the paver was placing to what it was told. The mill surface came up because it didn't use any 3D technology. So I went up to the engineers and basically started bugging them, trying to ask them what the structural benefit was of this material. It just looked like somebody just dragged something underneath their boot and scraped it on the surface. He was pretty angry at me and walked away, and I wasn't going to let it go away that easy, so I kept following wherever he went and kept asking what the structural benefit was of that. And he basically said, well, there wasn't anything, like we all know, and he basically asked me, how could we solve this? And I said, you could solve this with 3D milling, setting it to grade, getting your foundation proper, and then coming back and placing your material on top to have a more uniform surface. And that includes where they may have also milled a little bit more material to help control that. For whatever reason, they cut in here, and I don't know how the paving pattern ended up like this, but there was a lot of things going quite a bit wrong in building up this pavement structure. So other areas are incorporating 3D milling part of their operations. This is a project in Utah at the Salt Lake City International Airport. Everything in this surface, both coming in from the sides, from the taxiways, are all 3D milled, and it's basically uniform all the way through. Even where they had to mill a little bit more, filling it back up made it very consistent, and this is what we end up with, a constant structure all the way through. There's no leveling course or anything. It's just you end up with a much better structure that should last a lot more longer. So this has become a common term that I've been using, is you know, you can't fit a square peg in a round hole, and that goes back to the 2D milling part of it, and using 3D, it's very difficult, and we end up with not so good pavement structures. So another advantage of 3D milling, like I mentioned, is we can do variable depth and slopes if you need to mill a little bit more. It's not that we don't care what the existing surface is. You have a profile design to go to, and depending on your specs, you may have to mill a little bit deeper or not. And in this project right here, they had between 12 and 4 inches of milling. So depending on where they were on the project, they just vertically offset and just cut out these big rectangles and fill it back up with material. So this here is kind of looks what we typically see, where the surface may be milled and there's still waves left. Of course, the paver can put it down, you know, with averaging beams, even with 3D, it'll be placed very smooth. But after you roll it, we have what you call differential compaction, and basically you add another lift, and hopefully by the top lift, it's all nice and smooth. But what 3D milling can do is basically get yourself a nice smooth surface, so when you do place down your material, it's consistent all the way through. The same thing with leveling course. the contractor will go and fill in the low spots and then come back and put the constant surface thickness on. And 3D milling can help eliminate this leveling process by milling it to grade and just putting in your thickness requirement for your project. So some of the results of having better pavement structures using 3D, you end up with a much smoother surface, can handle and control vehicles at higher speeds, less impact, so the heavier loads don't beat up the road so much. Safer, you get better drainage, less ponding, or hydroplaning, better traffic control. The Quebec Ministry of Transportation invited us in a couple years ago to talk about 3D milling and how they can better their roads in the province of Quebec in Canada. And interesting enough, one of their first projects that they did, it was a part of the highway just east of Montreal, and there was an off-ramp. And you don't hear this very often, but the project was done so well and so safe, both from the 3D milling and 3D paving operations, they increased the off-ramp by 10 kilometers an hour. It doesn't seem like much, 6 miles per hour, but I'm still trying to find another project like this that they felt it was safer to increase it. But this is a direct relation to using 3D technology on their project and increasing the off-ramp speed. Also, better structures will give you longer lasting roads, hence lower maintenance costs, better snow removal. So if your roads are rough, the snow plows beat them up if you're in those type of conditions. And I don't know about you, but taxpayers enjoy driving on smooth roads. We always hear about the rough roads. We don't always hear much about the smooth roads, unfortunately. So here's an example. You guys can, work out with your own numbers, but I just put some numbers together on what a 1/4 inch of asphalt would cost. But just on a project that's about 10 miles, 25 feet wide, 4 inches thick, compacted, with your target asphalt density and about 150 tons place cost of material, will work out just about $4.8 million. Placing an additional 1/4 inch of material is about $300,000, just a 1/4 inch. So it adds up if you can help manage those materials. And additional costs would be any string line, so you don't need any for if you're using 3D. Any additional material costs, additional for leveling costs, that is, and any milling or grinding afterwards if you didn't meet your smoothness spec. And the positive side, if you are in an area where there are smoothness bonuses, you can increase that a bit. And I'm going to show an example of a project that was done in Oregon. How am I doing on time? Good? All right. So just a little quick overview on what we do for 3D, specifically on milling. We're basically a position sensor. We work no different than the wire sensor on the end gate or a sonic. We basically send raise lower commands to the mill following off of a design. So typically you'll have your wire ropes, your sonics, or averaging beams, contact sensors. They feed down through the existing machine system and control the legs to raise lower them. 3D does the same thing, but instead of being from ground up or referencing the ground, we use everything relative to a design, so basically it's top down, ignoring what's on the existing surface. Here's a list of our machines that we work with. Verken machine, Level Pro, Mobile-Matics, the Rotec ACE grade and slope. Mobile-Matics, we see them more common on Rotec machines. So the ACE is their newer platform, I believe, and you can talk to your Rotec manufacturer, but it's like their new E-Series. They came out about a year or two ago. And the CAT grade and slope systems on the CAT machines. These are the components that we have. We have a display, a target. This is an alarm on the machine. It's very loud. It actually becomes one of the most popular devices on the machine, because if they end up going off design or something happens with the 3D, this is extremely loud and draws attention to somewhere on the 3D. So some of the contractors tell us that that becomes their most popular thing on the machine. We also have a gyro sensor, power module, a radio for communication with the robotic total stations, and this is what the harness looks like to plug everything in on the machine. All right, the last part here is an Oregon DOT milling project. that was done in 2009 with, I think, Tidewater contractors in Oregon. So if you're thinking that this is the future, take note of the date. This is what happened back then. So, you know, this has been happening for a while. It's just who embraces the technology today based on the title of my presentation. But we've been doing this for quite a while. This project was 2 parts. It was a reconstruction, 10.5 miles of the road, milling between 5 and 8 inches in depth. And they also had a complete rehab or notch widening about 3.2 miles where they had to mill all the way down to finished subgrade. They use a rover, so this is where the mill, you can see that little target that I showed earlier on the mill, and then they have a rover behind checking. They were checking grade within 0.028, which is about 9 millimeters, but also take note on how accurate the control was. It was at the 1/4 inch. So, you know, we will get out based on the information that we have on the project, but overall the results were extremely tight, you know, basically into the thousandths of a foot. This one here, this is the existing road right here, and this would have been what they say the bottom surface original asphalt, and then this is what the design is right here. So using the 3D milling option, they can cut straight away to design, no further grader work required. In comparison to fixed step milling, they would have tried to follow this line, and if I remember correctly, they did do this with 2D, and they ended up overcutting and had to come back and regrade it to get it right. But the goal with 3D was to follow this profile design here and make the road smooth and basically one cut. And this is what it looks like. They did about 4,000 feet of grade, milling about 4 to 12 inches in one day. This was basically the fixed depth milling, so 2D, not 3D. And this one explains where the original road is here. This is the bottom surface original asphalt. And the actual 3D design, but the fixed depth milling line where they ended up. So they ended up, you know, cutting a little bit more and having to fill it back up and grade it or fill it up with a paver to make it level for the final lift of asphalt. The notch widening or the rehab that they did, they basically milled it all out, and then the surface that they were milling, they removed it and actually dumped it inside the notch to fill it up with the material from the existing roadway. And then they came back with a grader with the same technology, the same total station technology, and regraded it and got it all ready. So pretty efficient at fixing up this road. Here are some of the value engineering costs that they had. Again, the PowerPoint will be online so you can look at the details, but there was a lot of cost savings. The total contractor savings, including they had some rain delays, but they also finished the project 11 days early. So the contractor saved about 120 grand. And of course, the saving in the days was priceless considering the conditions that they were up against from rain and all that stuff. And here's more of the details of the smoothness bonus that they got. It was about over $127,000 that they got. So not only a cost savings in the operations used in milling, but also a bonus for their ride spec. Not too bad. I got to go. Any questions?
Right.
Yes, sir.
So what is the compatibility of this with the conventional design programs of the various agencies that are using, like the profiles and cross-sections? Like how much work is it programming into the machine?
That's a good question. So the question was, you know, various agencies have their own software creating designs and cross-sections. Some agencies are better than others, like Minnesota DOT, they will provide the design to the contractor. We have the requirements like I listed before. The unfortunate part is that there's still a lot of red inking going on, and what red inking means is that somebody builds an awesome model, and then as it gets towards a deliverable, the text items on the plans change, so that ends up being what is required to follow the paper plans, but the entities or the objects of the design are not matching what the plans are. So it's important that the process continues in 3D, and we talked at the Intelligent Construction meeting a few weeks ago that it would be great that people could build without plans, not having the plans and using electronic data. That would put a lot of responsibility on the owners to build proper models. So with that said, it's not uncommon for us to get information, bring it into our software, review it, compare it to the plans, and make sure it's right. That's a process that, in all my years of doing this, that I wish it would go away. So again, there's some agencies that are very good, and they basically stand behind their designs. The contractors will bring it into the manufacturer's software to make sure that it's ready for the machine, because we all have a little bit of different formats, and we do little things a little differently, and that's okay. But having to sit there and take the information from the agency, hire a model builder, take the set of plans, and spend a couple of weeks, in essence, putting the design back to where it should have been, is a lot of work, and it's a lot of responsibility. So we hope by educating a lot of people that they take more ownership so that we can see better deliverables in the field built for automated machine guidance. So it's not happening everywhere, but it is slowly changing.
Yes, Brian, have you had a chance to measure the ARRA before and after using your approach on, but measuring the ARRA not on the finished product, but measuring the ARRA right on the milled surface?
Oh, on the milled surface prior. That doesn't always happen just out of production convenience. Our goal is to be as close to zero as possible, reflecting on the actual design. Usually what happens is that contractors will do it on the first lift of asphalt if they have the tools to do it, and then we see the results out of that they're basically really, really good to perfect. Not that I'm aware of on the milled surface. So that's a good question. But again, reflecting on the material being placed down and the consistency in the cores and the ride on the asphalt, we know that that subsurface was done correctly. But I don't recall any data actually going out and checking that milled surface. Sorry. That's a great question, and I'm assuming you're a custom milling company? Agency? Okay, so Darren can actually probably explain this better than I can, because he was a subcontractor, and you do get paid by the square yard. That's traditional for mills. And they were hired from Staker Parson, who owns Western Rock, who had the great success with 3D. So Darren had to go into 3D, but he can explain probably better than I can, knowing how that happy medium comes in there to get quality versus quantity. You want to take it?
Trying to change it to a volume instead of an area, so go square yard inch, and that's easier to quantify.
Good. Thank you, Darren. Yes, sir.
Can you use this with multiple mills or smaller mills to do multiple passes, or you just have to have one larger mill to do this?
It depends on the operation. Oakland International Airport, actually Mr. Don in the back, Matthews, what do you guys have, 6 mills out there? So it got pretty complicated, but they were very successful in milling. So there is a limit to how the size, even though I think some people have attempted to put on small rear drum mills, but we're looking at production mills, I would say 6 feet and up. So some can go wide and get more accomplished depending on what their task is. Some people only have so much wide, but we don't, as long as it's a production mill and we can make a change on that surface, we're game to put it with 3D, but it just depends on what that machine is. And I haven't done it on very tiny machines, and maybe that probably answer your question. So does that answer? Yeah. Anybody else? All right, well, thank you for the opportunity. Again, it's a great honor to be here, and hopefully you guys can think about this in your process if you guys are looking at rehabilitating or fixing your roads. Thank you.